Get you going here. It's Easter weekend, everyone took off early. So where are we kind of currently at? What's due at the end of the day tomorrow? So we've got that fifth problem set and that fifth quiz. Okay. So that'll be over some the stuff that we've covered before, which was interaction terms. And I think the last couple questions or last one or two questions is about some of the early data kind of issues we talked about, some measurement error. So what we've got kind of finishing up today might bleed a little bit into next week, probably not much. It's panel data. And then we're going to talk about instrumental variables next week, and that'll kind of bleed over into that week right before finals. And that week before finals, we'll be primarily doing review in class. Okay. So next week, we're going to have one more in-class quiz. That's the last one that we'll have. After that one kind of passes, I'll update Canvas. According to the syllabus, I'll drop the two lowest. So I'll kind of give you an idea about where that in-class quiz grade is currently at for you. Looking at the quiz grades, and I'll kind of hold off until I see what happens with this fifth quiz. I'm going to have a sixth quiz and a sixth problem set. So I'll probably, after class today, I'm going to post that sixth problem set. I'll hold off on that sixth quiz until after Tuesday's class. So that problem set is going to be covering panel data and then instrumental variables. So I want to get out there early so you can start working on it early so you don't have to work on it all that exam or that week before exam week, right? If you kind of work along with what we've covered, you should be able to complete about the first half of it based off what we talked about this week. And then the next half will be what we talk about next week. So I'll have it up there while we talk about it. So if you want to kind of work along, you can kind of save yourself some time to have that week before finals to really focus on studying for your exams, okay? So you'll see that sixth problem set pop up this afternoon. Now the sixth quiz, I was feeling nice until I saw how many people are here today. But I'm still feeling kind of nice. I kind of look at where the average on those quizzes are and kind of where I want it to be. The sixth quiz is likely going to be pretty much survey based. So I put up a set of practice questions or sample questions like I would for the other quizzes, but I'm not going to give you a quiz that's related to that. So this will be helpful in studying for the final. So that's why I still put that material up there. But that sixth quiz that I will post next week is basically going to be kind of be asking you questions about the class, what you want to see reviewed for the final. It's really going to be primarily opinion based, and basically you can get all the credit, all 20 out of 20 points if you simply complete every question. Okay, so giving you a little bit of a boost, a little bit of a bump there with that sixth quiz. Now, I'm not dropping your lowest or anything like that, so still take this fifth one very seriously. That's due tomorrow, but as a way to kind of pull up that quiz grade, I'll give you that essentially more of like a graded survey right next week. Okay. But that problem set, that's going to look like the other problem sets. You still have to kind of get, graded for correctness. I'll get that posted as well so you can start chipping away at that. Okay. Other than that, any other questions for me logistically before we jump into material here today? Okay. So we left off thinking about panel data. So this was, we have multiple subjects and collected at multiple points in time. We said one thing we can do is use this first differences approach, where instead of running a regression of y on x, I take a difference in y from one time period to the previous, and I run a regression for the difference in x from the current time period to the previous. What that would do is essentially, and I had like the long form written out, I wrote it out for you last class, but it cancels out these, what we said were time invariant factors, things that were specific to whatever the subject was that don't vary over time. So by doing the first differences, we essentially can eliminate all the omitted variable bias that would have come from these time invariant factors. Okay. So I think I showed you how to do this in Stata. That's kind of where we ended. What we can also do is include fixed effects. Okay. So I'll give you somewhat of an insight. Really, technically, we've already done this. Okay. So if I have a regression where I'm trying to predict some y variable and it varies with subject and then the time period. Okay, so we usually would have kind of this intercept. We would have this x variable that we're interested in. And then here we can think about what if I had, let's say, I think my example that we did last class was like countries, right, and their GDP. So let's say we had time invariant factors that they were the same for one country, but they varied across countries, right? So maybe there's, a certain factor that's always the same for the US, but that varies from a factor that's always the same for China. And that varies from a factor that's always the same for India, and et cetera, right? So we've got these time invariant factors, right? Now, this isn't going to be specific to just, everyone's going to be a little bit different, right? China's is different than the US. So how could I pick up this X variable? This is going to keep changing across time. But if there's factors that would vary with each country, I could almost think about it this way. Let's say my Y variable, I'm trying to predict GDP, and I don't know, I'm doing something like health expenditures, right? So that's the coefficient I'm interested in. When I'm thinking about my line of best fit, what's one way I can allow for my predicted GDP to vary with countries? What could I include? So if I think, for example, we typically would do something like, maybe I had, is it considered a developing country or a developed country? What would I do to capture that difference? So it could include interaction term if I thought this effect varied with that. If I'm just thinking about, I'm trying to predict GDP, and I think that it has a different starting point. So maybe I think the effect of health expenditures is the same for developed and developing countries, but I think that maybe the starting point of GDP might look very different. All I would have to include, in order to do an interaction term, I would have to also include this, would be a what? Dummy variable. So notice these things, if they're time invariant, what we're really saying is each country has a different Z value. So what I can do is essentially, I would have like, here's country US, right? And then just include a dummy variable for, is it the US? And then China, dummy variable for China. That's what this variable is capturing, that there's a time invariant factor for every single country. Now it's time invariant, so it's not changing across time. So all I really need to do is include a dummy variable. So now it's like, where does the US start out? It would be like beta 0 plus the coefficient on the US, beta 0 plus the coefficient on China. And then I would kind of have my different lines of best fit. Now, what do I still need to do? So if I have every country, if I'm including dummy variables, it's categorical in a sense. We said we always need to do what? Well, this is the predicted increase in whatever this Y variable is, GDP for the US, relative to what? What group am I comparing to? So every group I leave out. So if I want to capture the fact that every country has maybe a different starting value, I would include a dummy variable for all of them except for one of them, right? So I would need to still leave one of the, so basically, when we're going to do something called fixed effects, it's essentially just including a dummy variable for every possible value for this variable Z, right? So every possible country we could see, we're just going to include a dummy variable and leave one of them out. Okay? So we've really already done this before. We're just going to look at it in a slightly different context. So we're not going to do this yet. We'll kind of set this up. Go to our do file. Got my global. We did first differences last class. I'm going to use this birth data by state. So down here where it says fixed effects. Now, one thing we said last class, so I've got all this data, a bunch of different states. It's got their number of births, the average age of the mother, and the average birth weight, right? So every state, multiple points in time. Now, I would imagine I probably have every state recorded for every year. So we talked about if we have a balanced or an unbalanced panel data set. Balanced is if I have every single subject for every single year. So maybe I'm missing a couple states for certain years. I don't know why that would be the case, but maybe I am. There's a quick way. I don't have to go through this by hand to check. We said we can create this variable. It's just a 1. Then by each subject, which here that's our states. In my other example, that would be by country. I'm going to add up all of those 1s. That'll tell me the number of years, right, that I had information on those on those states in this example. If I then use the tab command, that tells me kind of what the values I have for this total year variable are. If it's a balanced panel data set, I should have 6 years of data for every single state here. In fact, how many states do I actually have in my data set here? If it's 6 years for every state, 306 divided by 6 would actually be 51. I'm guessing it's like DC. I'm sure it's Washington, DC, or maybe it's, I don't know, American Samoa, or one of these other territories. So we have all 50 states plus, like I said, I think it's probably DC, right? So I could run this regression where I look at kind of the average birth weight of the mother and the average birth weight of the mother, average birth weight of the child and average age of the mother, right? So I'm going to run this regression and I come up with a coefficient of 14.8. So for every additional year older that the average mother is in a state, we would expect birth weights are about 15. And here I think it was probably what? Let's say, I think it's grams higher. So looks like maybe the older you are, kind of slightly heavier babies you have. Typically birth weight is a good thing. This might be the idea that you're waiting a little bit longer to have a kid. Maybe you're a little bit more prepared, right? And maybe you're doing things during pregnancy that make that child healthier or heavier, right? That's not always better that's heavier, but right, when the values we're looking at, typically birth weights are a good thing. Higher birth weight, sorry. So we think that maybe there's something that varies across states, right? So I used kind of some stereotypical examples, but like if I'm using a state like Utah, my guess is just based off of the religious breakdown of that state relative to the entire US, right? They might have kids at a slightly younger age, right? If I'm comparing it to something like New York, right? Where people typically, I mean, I don't know, there's like TV shows, right? Of people far into their 30s without kids, right? So maybe there's some differences across these states. So I could do what we've already done, which is use this IDOT command. So the IDOT command put in all those dummy variables and it kind of chose one to leave out for us. So we didn't really know it, but when we were using that IDOT command to include dummy variables for a categorical variable, we were really already doing, well, fixed effects. Now the problem is when I tried to run this, I'm getting an error because, oh yeah, state is a text, right? I can't include text into a regression. So what I need to do is we said we had that encode command. So one way of getting around that was say, just take that original variable, create another variable that I can use in my fixed effects regression. When I encode it, it takes every name and it assigns it a unique number. So when I run this command, we've used this before. What that encode command did is it still looks like Alabama, but Alabama's a 1. And then Colorado's a 6. And then, yep, here it is, DC's a 9, right? So it's basically giving me a numerical value so that Stata can actually start to do things like use that IDOT command with it. Right? It's not a text anymore. It looks like text in the data, but it switched to blue. Every text kind of has a corresponding number. Okay? So now when I run my regression, there we go. Notice it includes every single state has a dummy variable. Now here it left one out. The problem with it, if I do it this way, I don't have any idea what state it left out here, right? So all of these coefficients are relative to, well, it looks like maybe just looking at it, looks like Alabama got left out here. I kind of lucked out. It was one of the first few states that I can recognize isn't in there alphabetically. But you can imagine a different example. So like I've got some player shot data. I'm not going to have any idea which player it left out if I include player fixed effects. I can't hunt through the data and figure out who it left out, right? But we usually don't care, because if what I'm really interested in is the relationship of the mother's age to the birth weight, all I care is that I can control for these these state level time invariant factors, right? I'm not really using these coefficients to make I'm not really as focused on them. I just want to make sure I'm controlling for those things, okay? So that's kind of our first look at fixed effects. Is this sounding familiar to things we've already done, hopefully? Right, we're using that IDOT command. We're just including a bunch of dummy variables. Now, there's another way of running this. And I'm going to try to do this from memory. I probably should have looked this up. But you can run it using this areg command. The thing with the areg command, I believe it's the most useful when you have really large data sets, because the way in which it does all of the math behind the scenes. So I've kind of punted a little bit in this class. Like when you have more than one variable, and when you have like all these dummy, really what algebra is being done to come up with this line of best fit is like matrix algebra. And it can bog down the computer, right? When you have a lot of observations. So this areg command is a way of like, if you have a lot of observations, it doesn't quite include these additional controls. It kind of calculates an average, which we'll talk about in a second. We'll kind of actually look at this, what it's going to be doing behind the scenes. And it can sometimes just run a little bit better. So all you do here is you use areg, and then whatever you wanted to use the I dot command for, you just use the A in parentheses. It does the exact same thing, just a difference in syntax. So you'll kind of see, what do I get? Negative 33.4, no matter which command I use. Now notice, if we compare that to when we didn't include fixed effects, we're not only getting a different coefficient, it's a completely different sign. It's more than twice as large, and it's a completely different sign. So here, this was, if the average age of the mother is a year older, birth weights on average go up by about 15 grams. But now, what's my interpretation of these results? Every time the average age of the mother goes up by 1 year, the average birth weight goes down by 33 grams. And what do I get to add in at the end? Holding all else constant. What am I holding constant here? What state they were in, right? So that's a lot more powerful of a statement. I've eliminated a lot of omitted variable bias. It's going to come from these time invariant factors specific to each state. Now, I'll point out what's one other thing that's kind of nice about this areg command. I don't have to look at every single state in my regression. It absorbs those. That's kind of the idea of like A here, it's absorbing those state fixed effects. So it's not showing them to me. So it's a little bit nicer to look at the output. You can imagine with 50 states, that's not a huge deal to scroll through that. But if I'm doing like that player shot data across 20 years, I don't want to scroll through every single player's name, right? That's just going to take me forever. So that areg command can be kind of helpful. Okay. I'll also point out, so my standard error here is 3.54. 3.54 here as well. Right. Oh, where is that? There we go. So it hasn't really done anything to our standard errors either. Still calculating it the same way. So just a nice kind of a little bit easier way of looking at things. Okay. Now we have a third way of doing this, which will give us some benefit, probably not from things we'll talk about today, but we might use this a little bit next week, which is I can set my data set up as a panel data set, and then I can use some slightly different commands. So xtset is essentially telling Stata, I want to set this data set up as a panel data set, and I'm going to tell you what the subjects are and then what the time periods are. Well, my subjects here were the states, so I'm going to use that numerical state variable that I created that identifies who my subjects are. And then for each subject, I've got multiple years recorded. So it doesn't look like it does much here, right? Now, one thing that's kind of interesting, and it doesn't tell me if it's perfectly balanced, but notice it'll actually mention whether or not it's strongly balanced or not. So when we look at some of the other data sets and we'll use this xtset command, it quickly will let me know like this is a very unbalanced data set, right? I don't even have to kind of use the other method that we worked through. So here I've got it set up as a panel data set. What I can now do is use not the reg command, but xtreg. So this tells it run a regression with panel data. And what I want you to do is include fixed effects. So FE is fixed effects. All fixed effects are a dummy variable for every single subject, right? That was our state. That was the thing where we thought there was things specific to each state that don't vary across time. We were using state fixed effects. So once I set this up with my subjects as the state, time period is the year, I run this xtreg, and then I can kind of say just comma FE. It automatically knows to put in state level fixed effects, and look what I get. The exact same coefficient as if I use the other syntax. So it's just really 3 different ways of doing the same thing. Now, another advantage here is, what does xtreg not show me? All of those dummy variables, right? So, and also we'll have some additional things that we might talk about here in just a second, or next week if we don't quite get there today. I shouldn't say a second, maybe later today, maybe not until Tuesday. But we've got some slightly different statistics up here than the regular reg command where including like the I dot showed us. Okay. But ultimately, same coefficient. So all 3 of these, oops, scroll up a little bit. All 3 of these show me the exact same results. Okay. Any questions on that before we keep moving here? Does that make sense? Now, once again, if I am interested in like what state is the highest and what state's the lowest, I can't tell from this output. Right? I don't even know what state was left out. Right? So if that's really my focus, I can't really, I probably don't want to use these xtreg commands because I'm not going to be able to identify what state had the lowest or what state had the highest coefficient here. Fourth way of doing this. All right, so we'll go back to the slides before we do this. Now, I'm not going to make you reproduce this math. I'm going to show it to you to prove it to you, and then we'll prove it to ourselves with data, okay? So if I were to write out my regression where I've got this kind of alpha I, so what this is going to represent, we go back here. If I was moving from a simple linear regression to one where I included dummy variables for every state, I could almost think about it here as like alpha I is going to capture like the starting point for every single state. So if I come down here instead and think about I'm running this regression, if I take the average y, that's just going to be an average of this function. So I would take the average of everything. Well, the average of my error term really should be, I don't exactly know, but expected value of my error term, we said, should be 0. And then here, if I take kind of what that beta 0 point would be, it's the same for every state. So the average of that should just be itself. So notice the average y is going to be that same linear function of the average x variable. So if I take my actual regression, actual y variable, subtract the average, I could write that out and just plugging these two equations in. What I'll notice is, oh, this constant cancels, right? We kind of had here, the expected value of my error term here is 0, so I'm just left with my error term. So the change in y is going to be equal to beta times the change in x. That was our first difference regression. Okay? So what we can do instead is, it looks similar to our first difference regression. So what I can do instead of like using all these commands like built-in xtreg and idot, if I take the actual y values and subtract the mean, right? So if I subtract the means here, what we say d-mean the data, I should end up finding the exact same coefficient. Right? So like I said, not going to harp too much in the math here. We can kind of plug things in, see what cancels. I think another kind of a nice, easy way to do this is prove it to ourselves with data. Okay? So I'm going to go back to that data set we're working with. I'm going to generate two new variables. One, and here it's not going to be, I shouldn't say this. When I say d-mean the data, I should also be a little bit careful. I'm d-meaning it not from the overall mean, but from each subject's mean. So I'm going to take Alabama's data and I'm going to subtract Alabama's mean across those time periods. I'm going to take Arkansas's data. I'm going to subtract Arkansas's mean across those time periods. So notice here, I'm going to create this birth weight mean variable. It's the mean of the birth weight, but I'm going to do this by each state ID. So for every state, I'm going to do the same thing for the mother's average age. So if I run this, I'll kind of show you what that is going to look like in the data. Notice for Alabama, we've calculated the average birth weight and the average mother's age. Notice then when I go down to the next state, Alaska, I've calculated Alaska's average birth weight and average age, right? Or mother's age, I should say. And then kind of so on and so forth. Right? So what I'm then going to do is create two new variables. One where I take whatever that y variable and that x variable was. So we had birth weight and mother's years of age. And I'm just going to subtract that state's mean. Right? Those were the variables that I created, were the state level means. So here, birth weight minus the average will just be that state's average birth weight in that year minus the average across all time periods. And then age minus average will be that state's average mother's age in that year minus the average mother's age across all time periods. Okay? So d-meaning the data by each state's mean, I've now created these variables which give me each state's kind of y values minus that state's mean, okay, across all time periods. Okay. So hopefully, unless I'm lying to you, once I run this regression, where I'm now using the d-means data, I'm using the birth weights minus that state's average, mother's age minus that state's average. Hopefully, I see it's the exact same value. Otherwise, I'm making something up, right? So I run, sure enough, I get that exact same coefficient. Okay. So by demeaning the data, I end up kind of with the same coefficient here. Now, I am going to have a slight issue, which we won't really dive into why in this class. But if you were to kind of continue, you usually would see, if you like look at academic papers, the way they would code this, they would actually rely on using like that XT-reg. If you demean the data, there's some stuff that's going on that's a little bit outside the scope of this class. But notice what's happening to my standard error when I simply demean my data. It's not quite the same. So notice when I demean the data, I'll find the correct coefficient, but what might I make the wrong decision in regards to? If my standard error here, it's a little bit lower, so what would I be a little bit more or less likely to do? Reject the null, right? So it could screw up my rejection decision if I use the demean approach. Now, there's ways we could get fancy. One of the things we didn't actually do there, maybe the error's there because it does vary across state. I should have actually been like subtracting the mean error. And so we're not going to go through all that. All I want you to know is if you demean the data, you end up with the correct coefficient, unbiased coefficient. But our statistical significance could be a little bit off. Okay. Any questions on this before we keep moving? Okay. Did I copy paste the exact same thing down here? I sure did, right? Oh, no, I didn't. I know what I wanted to show you. All right, so that was that example. Now, what if I think, and this probably isn't as likely, but let's think, what if I think that there aren't as many state level factors that don't vary across time, but I think that there's more time factors, right? Or how should I say this? So there weren't as many state level factors that didn't vary across time. There's more time varying factors that don't vary across states. So like 2006 had very different conditions than 2007. And 2007 had very conditions than 2008. What we were doing before is we said Alaska has very different conditions than Utah, than New York, et cetera. So if I instead think that the variation, that things that are constant across all states, but within each time period matter more, what would I want to include? Not state level fixed effects, but time level fixed effects, right? So it would really be the exact same thing, right? So what I could do is I could just use the IDOT command. Now, instead of the state, I'm looking at the year. I could use areg, same regression, but now I'm controlling for year fixed effects. Now, if I want to use the XT set, before, when I set it up as a panel data set, I first tell it what the subject is and what the time period is. Here, the thing that I actually want to include fixed effects for, my subject, is actually the year or the time. Now, so you wouldn't typically do it this way. Most panel data sets, we do it like subject by time. But if you did think that the time invariant factors across states matter more, I could set it up with year as my subject and then the states as kind of my time periods, right? So if I run all three of these, hopefully, once again, they're all including these year fixed effects. So notice here, it's got year fixed effects. You get my coefficient of 18.22. 18.22, exact same coefficients, no matter which kind of way I code this up in Stata. Now, what was the original? Remember the original coefficient we found without any fixed effects was like, what, negative, or no, it was positive 14, I think. So we're getting a slightly different value than what we originally started out with. Okay. You could also demean the data. I won't waste too much time on this, but like, now, instead of calculating the mean for each state, I'm going to calculate the mean for each time period and then subtract that from my X and Y value. So if I do that, I get that exact same coefficient as well. So it doesn't matter which of these four ways we use, we should still come up with the same unbiased coefficient. And I say unbiased, at least in the sense that we've controlled for whatever this fixed effect is. In our first example, the country fixed effect. Second example, time or the year. Okay. Now, before I keep moving, are there any questions on that? Excuse me. Okay. Well, what do you think in practice? Do you think that there's things that probably are constant across states within the same time period? Are there things that are constant in a state across time periods? There's probably both, right? 2006 economic conditions is very different than 2007 and 2008, but there's also very different demographics of Utah versus New York versus Texas. Right? So we can actually do something called two-way fixed effects, right? So the way that I'll kind of show you how to do these in the sake of for this class, what we can do, I can set this up as a panel data set. Here, I just set it up with my subject being the state and my kind of time period being the year. That's typically how you would think of panel data. But if I think that there's things that are the same across all states within the same time period, maybe I don't just want to include my state fixed effects. Maybe I also want to include year fixed effects. How can I do that? Just use that IDOT command. Okay. All right. That would include a dummy variable for every single year. So now what this will do, and this is where it would get very complicated. If you wanted to do two-way fixed effects, you would actually need to demean the data by the average of the state and then also the average of the year, right? So you're doing a lot more work. If we simply set this up as a panel data set and use the IDOT command for our time period, that xtreg saves us a lot of coding, right? All we have to do is set it up as a panel data set. Now it can include two levels of fixed effects, both state and time. So now we're controlling for even more. So if I run this, notice, oh, why didn't it like this? So I've got, it'll look like it's dropping these years, but right, what I can essentially do, where's that? There we go. Oh, I know why. Sorry, I was like, wait, this should be working. I forgot to reset the panel, right? We're setting it up as state is my subject and year now. So if I do that, now I run this line of code. There we go. Now it's including state and time fixed effects. Notice now I don't get 18.2 or that negative 33. I'm getting a completely different coefficient. In fact, once I can control for the state and once I can control for the year, what does it look like the relationship between the average mother's years of age and the average birth weight actually is? I can't say that it's statistically any different from 0. P-value is like 0.6 here. I can't reject at any levels. So we're kind of thinking about going for the most naive regression. Do I include only one level of fixed effects, either for the state or either for the year? I'm going to get very different coefficients because doing each one of those fixed effects only controls for that thing. If I use two-way fixed effects, I'm now controlling for things that don't vary within a state across time. And I'm also controlling for things that don't vary across states within the same year. That's a lot more. I'm controlling for a lot more. And it's hard to think about these two-way fixed effects. Hear me say that, right? It's conceptually hard to think about it, but we're really controlling for a lot more, right? That's the end of the story, and we can get a lot more unbiased coefficient estimates, okay? Now, you could do this the exact same way. So if I set this up and used year fixed effects and then did the i.state command, I should still end up with that same coefficient. So I've got what, 3.75 in both scenarios. They're both doing the same thing. It was just doing it in a slightly different way. Now, what's one advantage of choosing to do that FE command with my states as opposed to doing it with years here? I had a lot fewer years, so it just made the regression output that I had to look at, I don't have to scroll through as much, right? But yeah, that is kind of everything. We kind of think about the ways that we code up these fixed effects. Anything else I want to say here? I don't think so. Any other questions before we move to kind of a second example, just different data set? So like I said, really a lot of this fixed effects is going to be very similar to things we've already done. It's just looking at it in a slightly different way. Okay. So let's now open up that GDP class data set. So that should be right here on Canvas. So I'm going to run this naive regression where I want to try to predict unemployment rates based off of income. I believe this is state and county level data. Okay. So here I'm going to run this. Okay. Now, got kind of a problem. And I wouldn't expect you guys, I wouldn't push you this far like on your problem set, but I want to start to introduce at the end of class things that you would see past this class, or if you were working for a firm. So I've got every observation is a time period, a state, and a county. So notice I've got Alabama, but multiple counties, multiple time periods. So if I was setting this up as a panel data set, and I tried to set this up and say, well, look, I've got my states. Within the states, I've got different counties. And for each county, I've got 6 or 7 different years, whatever it was. I can only use 2 variables when I set this up as a panel data set. So what's one thing I could do? Instead of setting it up by state and county, every state and county, I could assign a unique number, right? That way, you know, I don't know, Monroe County, Indiana is always a 1. Well, Owen County is always a 2. And then some other county in Michigan is always a 50, right? I just kind of assign each one. So that way my subject is still state county, but I only have 1 variable, so I can set it up as a panel data set like that, right? Now, once again, I wouldn't expect you to kind of do this on a problem set, but if you use this gen command, this was actually going to put a 1. So this will put a unique number, this syntax. For every state county, the first observation, it puts a 1. So new state county puts a 1. New state county puts a 1. Okay. The next line of code, what it will do is it'll sort those so that every time I have that kind of first observation, it's going to set this up so that it's going to start to do _n means start with 1, then put a 2, 3, 4, 5. So every time I have the first observation of a state county, what this will do, for Pawnee, Oklahoma, it puts a number. Then for Columbia, Wisconsin, that's a county and state. It's giving each county state a different number. Now, that was only going to be true for the very first time period. For every other time period, I've got a bunch of missing data. So what I could then do is say, well, look, I know that by each state and county, I just want to put in whatever that variable, whatever that number was that I assigned to that variable that was in the first year. So I can then do that. And now I've got this state county, Wyoming, Crook, Wyoming, is 2,511. Natrona, Wyoming, here. In fact, we could even, we could find, oh, did I drop state here? I did. I was going to say, we could sort through this. Let me see. We could find Monroe County, right? So we've got Indiana. Where's Monroe County? Every time we have Monroe County, Indiana, that's going to be a 690. Right? So I now have a number that's associated with each combination of state and county. So now I can set this up as a panel data set. Right? So I've created this new variable, which is a unique number called state county. I could see if it's balanced, kind of the same way we did before, create this new variable. It's just a 1, by the state county ID, add up the number of years, hit tab. Hopefully, if it's balanced, that should be the same for every single state, right? Sure enough, I've got 7 years of data for every state and county combination. Now I'm going to set this data set up by state county. That's what I originally wanted to do. I just can't do that if it's 2 separate variables. I had to create kind of this third placeholder. Right? Now, once again, if I were to give you this data, I would give you this variable already created. But I'm just kind of showing you like some of the different things that you can do or code up in Stata. So I'm going to set this up now. I've got state county as my subject. Time period is the year. I can use that xtreg command to estimate this relationship, including fixed effects. I think before with a naive regression, what did we find? Negative 0.07. If I instead come down here, where was I at? Use my fixed effects, right? Now I see instead of negative 0.07, negative 0.24. That's an even larger negative value. And that's because now I'm controlling for the state and county that the data point was in. It's a lot more powerful of a statement, right? Anything that is specific to that state and county across time, I'm controlling for that, okay? So that's going to control for a lot of like socioeconomic differences, demographic differences. And I don't even have data on that stuff, but I can still control for it. And that's really powerful, right? It's hard to get data on everything. So if there's things that I think are time invariant using fixed effects, I don't even need to get data on it, and I can still control for it. And then we can also do two-way fixed effects here as well. So I can use those fixed effects, but also include fixed effects for the time period. Notice if I use that, I'm getting an even different value, right? So that's because I'm just controlling for more factors. I'm throwing in a lot of additional controls. I'm eliminating a lot of omitted variable bias by doing these fixed effects or then these two-way fixed effects regressions, okay? Any questions on that before we keep moving here? Is this making some sense, hopefully? Okay. All right. Let me think about where we're at on time. I'm gonna get you guys out a little bit early. So we'll do this, and then I think I'll do some more examples at the beginning of next class. So the next example data set we'll look at, we're also going to talk about something which is called autocorrelation or error terms. So you can kind of think about maybe this in the context. I showed you that doing like the first difference approach is similar to if we run kind of the fixed effects models. But when I'm doing a first difference, I would be taking this current time period's values minus the old. So I'd be taking this current, built into that would be this time period's error minus the previous time period's error. If those error terms are related though, well, then I automatically know when this time period's error is low, the other one's going to be low. And if it's high, it's going to be high. So the difference in those errors will depend on the actual value of whatever the error was previously. So anytime we have a correlation in our error terms, we're going to say, you know, to go through the mathematical proof of why this number, we won't waste time on that for the sake of this class. But if it's anything other than negative 0.5, we're going to have our estimates are going to be impacted, right? Specifically our statistical significance. So I kind of showed you earlier, like when we did the xtreg command, we noticed like the standard error fell a little bit from what the previous regression was. So it's kind of similar to something we already talked about, which is heteroscedasticity, but a little bit different, right? Ultimately, at the end of the day, it's an issue that we know might exist with our error terms. So when we had heteroscedasticity, what was one command we said we could use to account for that? Remember what it was? Starts with an R. We wanted to use robust standard errors, right? We didn't talk about what state is doing behind the scenes to do that, but it's adjusting for the fact that we had heteroscedasticity. Here, we might want to be able to adjust for the fact that we've got some what we call autocorrelation or error terms across time periods, okay? So instead of using what we call robust standard errors, here, we're going to use a command that's clustering the standard errors, right? We think that the error terms might be correlated within a state over time, so we're going to try to account for that. One way that's kind of built into Stata for us to do that is use this cluster command, right? Once again, we won't get into the nitty-gritty of exactly what it's doing. We just know it's going to adjust for when we do have this autocorrelation, okay? So autocorrelation is conceptually more difficult to think about. So we're just going to focus on a test we know can identify it, right? So the test that's going to identify this is we first think about, if I were to run that first difference regression, right? So that was kind of like we did last class. We're going to save the residuals, right? So we're going to save the error terms, and we'll see how we do that in Stata in a second. We're then going to run a regression where we look at the current year's residuals, or the current first difference regression residuals, and we run a regression of that on the lagged residuals. So if we do that and we cluster the errors at the subject level, we're going to leave out a constant. We need to do that in order to kind of pick up this correlation. We'll kind of see how we code this up in Stata. We then want to run a test to see, is that regression where I looked at my residuals as my y variable, my lagged residuals, or the residuals from the previous time period as my x variable, if that coefficient is anything different from negative 0.5, if I can say that it's statistically significantly different from negative 0.5, I have autocorrelation. And what do I need to do? I need to adjust for that. Okay. So how do we do this in Stata? I think this is going to be probably ask you fewer questions in terms of like on the quiz or on the exam. I already told you the quiz is going to be easy for this material. But on the exam, I would be less likely to ask you to kind of do this. I'd be more likely to ask you to do this on your problem set, right? So let's go down here. We've got, oh no, we were using the GDP data set, so we're just going to reload that data. I'm going to come down here, and we already talked about if it was balanced or not, two-way fixed effects. So here is how we're going to test to see if we've got autocorrelation. Okay. So I'm going to set this up. Now, one thing I don't think I showed you last class, I showed you how to do first differences. If we started out with a data set where it had 2007 and 2006, like in the same row. So one thing that's kind of nice, if I have a panel data set, so I'm going to set this up. Now I forgot I have to create this state county variable. So I'm going to set this up as a data set where I've got that state county unique number. That's my subject. And it's going to vary across time. Okay. So I've got it set up that way. I can now use these commands in Stata. So notice this capital L. What that does is it already has the data like behind the scenes sorted by state county and by time period. And L dot tells it, stay in the same state county and get the value of this variable from the previous year. So that's what we would call the lagged variable. Right? Lagged is always like one previous time period. Okay. So if I want to create the difference for the unemployment rate, I'm going to take the current unemployment rate and I'm going to subtract whatever that state county's lagged unemployment rate was. All right, so that's where that kind of capital L dot command comes into play. So I don't have to have all of the years in the same row. They're in separate rows, separate observations, but this is essentially going to give me that difference or that first difference in my Y variable. And then how do I find the difference in my X variable? I'll just take the current income and subtract the lagged income, previous year's income. So if I do this, notice what observations am I going to lose? So if I've only got 7 years, what happens? So I've got what, 2017 to 2011. When I try to find the first difference for 2011, what year would it be going back to? 2010. Do I have that in my data set? So what's going to happen to my number of observations? Every time I look at that first year, I can't find that first difference, right? So automatically I know when I'm using this first difference approach, why? So I introduced it to you last class. Why would it be preferable to use these fixed effects methods where we kind of set this up as a panel data set and include these dummies? Because if I use the first difference method, what do I lose? The first year of every single state county here. So if my sample size goes down, what's going to happen to my test statistic? It's going to get, so smaller sample size means the test statistic is also going to get smaller. Standard errors, right? So I didn't go through the whole thing. Smaller sample size, what happens to my standard errors? Standard errors go up. What happens to my test statistic? Test statistic goes down. Test statistic goes down. P-values get larger, less likely I can reject. So using that first different approach is not ideal when we're trying to estimate the coefficient, but it's what we need to use in order to identify autocorrelation. Okay, so we'll go back here. We've got that first difference or the change kind of in both variables. So here, what do I want? So I'm going to put this comment in here to remind myself to show you something. But I've already got these created. So what I'm then going to do is run that first difference regression where I take the difference in unemployment rate, which I calculated, and the difference in income. So we've used this command before, but usually we were doing it to make predictions for Y. So the predict command, we usually said like predict whatever we want to call the variable and then comma XB. So that told us take the values for X and the coefficients and predict Y for us. What we're actually going to want to do now is use this built-in command, which is tell us the residuals or tell us the errors or the difference between the actual and the predicted Y from this regression that we just ran. So our first difference regression, we're going to create this new variable called residuals, which are the predicted residuals from that regression or the predicted error terms. Okay. Remember, the error is just the difference between the actual Y and our predicted y. Okay. So we're going to go ahead and do that. So I've now got this residuals variable here. Okay. Let's go back to my do file. We said the test for autocorrelation is to then run a regression of the current year's residuals, or error term, on the lagged year's residuals. Okay. So I also have to include no constant. So we have never done this before in this class. It is not an option you would want to use in any other, like if you're running a typical regression, you always need that constant. But in order to do this test, since we're simply looking for like a correlation between the errors, we actually don't want to include a constant here. So there is a command you can use in any regression, which is to not include a constant. We just never, there's not really a place where we ever need to use it other than doing tests for things like autocorrelation. We're then going to cluster those standard errors. So once again, it's very similar to when we were using robust standard errors, and we're just going to cluster them at whatever the subject level was. So here that was state county. Now when we run this regression, I see that the coefficient between the current residuals and the lagged residuals is what? 0.11. Well, that's different than negative 0.5. But is it statistically different from negative 0.5? Well, what does the test statistic and p-value always kind of use as the default for our assumed coefficient value? If I were to run any typical regression, what do we start out assuming all the coefficients are? Yep, 0. This does too. So what do we actually want to know? We want to test to see if this is not just different from 0, but is it different from negative 0.5? So anytime you run a regression, if you are interested, so let's say like I won't push us this far or take us this far in the class, but let's say I'm estimating the relationship between hours studied and test performance. I know that it's not 0. I know that there's a positive correlation, but I might want to know, well, does every additional hour, does it not only increase it, does it increase it by more than 5 points? So I might want to actually change my hypothesized true value from 0 to actually be 5. Right? So we've kind of gotten away from this. We did this more when we were doing review at the beginning of the semester. So technically, we have been using this as our test statistic. Remember, anytime you come up with a test statistic, it's take that sample value or the predicted or the value that we found from our sample data, divide by the standard error. But what are we supposed to always be subtracting? We said the assumed value of beta. It's just that for us, we were always assuming it was equal to 0, so we've just been kind of ignoring it. But you can actually do tests against any value you want. Now, the regression output is only going to give us test statistics and p-value for the hypothesized true value of 0. If you want to do it against other values, like here, I'm going to say test that coefficient on that lagged residuals variable and see if it's just different from 0, but is it different from negative 0.5? That was our autocorrelation test. Sure enough here, I mean, slightly different. We're not looking at F or T values, we're looking at F values, but we can kind of use the same ones. And it also gives us a p-value. Is this p-value going to be less than any of our benchmarks? It's 0, so yes. So we can say statistically this is going to be different from negative 0.5. In fact, I didn't really need to run the test here, because what could I say that this coefficient is statistically different from? 0? Well, if 0.11 is statistically different from 0, is 0.11 going to be statistically different from negative 0.5? Yeah, it's even further away, right? So this is an example where I don't really need to run that additional test. I kind of already knew that. But assume that I found the coefficient was like negative 0.2. Okay, well, negative 0.2 might be different from 0, but it might not be different, or let's say negative 0.3. That could be statistically different from 0, but not statistically different from negative 0.5, right? Anything in between kind of 0 and negative 0.5 there, it would be a little bit trickier. But that's how you would run that test, right? Just test whatever variable you want to test the coefficient of. Not is it different from 0, but is it different from negative 0.5? In fact, if I use 0 here, what should I find? I should find kind of a p-value that matches up with what I originally found, right? Because that should be the assumed true value of 0. Yep. All right. Let me think if there's anything else I want to say here. One more thing, and I'll get you out of here. So we can reject that autocorrelation value is negative 0.5. So this gets kind of tricky. Remember, when I'm assuming, so if I did have autocorrelation, that coefficient I find would be negative 0.5. We just found a p-value of 0, so we said we can reject that. So what are we trying to test for? We're trying to test to see whether or not there's no autocorrelation. So we start out stacking the deck against ourselves, which is we assume that there is autocorrelation. So you almost start out assuming that you need to adjust for this. And then if you can find that it's different from negative 0.5, well, that means that you can reject that there's autocorrelation. If you say you're rejecting there's autocorrelation, that means there is none. You don't need to make any adjustments. Okay? So in this case, right, we found that p-value of 0. So we're rejecting that it's equal to negative 0.5, which negative 0.5 would represent autocorrelation. So we're rejecting that. We're saying there is no autocorrelation. So when I run this regression, and here I can do, I use the IDOT command. Why did I do the IDOT command here? Because I want to show you something different here. Doesn't matter. I think I did this to show you that there's a significant difference, but we don't have to here. Oh, actually, yeah, I'll do this. So I just included my year fixed effects as well here. I think it's because the values make it a little bit easier to see. But basically, if I think that there was, so I rejected there's no autocorrelation. If there was, all I would do is add on at the very end of XT-reg this VCE. So all I would do there is cluster my standard errors. Now you can kind of see an example where I don't cluster and then I do. So if I don't cluster my standard errors, it's getting what? 0.002, and I was getting a p-value of 0.3. Notice here, I'm getting the same coefficient if I cluster my standard errors. What's happening to my p-value? It's getting larger, right? So it's always going to make, it's going to make our p-value a little bit larger, which makes it less likely we can reject. But here, like in this example, if I didn't find strong evidence that there was autocorrelation, then I really shouldn't be adjusting for it, right? So I'm going to focus more on that you can kind of run that test or know what that test is, which is essentially using those lag commands, right? Calculating the difference for each variable, run the regression, that first difference regression, save the residuals, run a regression of the residuals on the lagged residuals, and then test to see is it anything different from, and I changed it here, but should be as any different from negative 0.5.
Is it always, you always test the negative 0.5?
Yep, negative 0.5 tells me that there is autocorrelation. So that's what I'm trying to reject, right? Hopefully, if I can reject that, that means I don't need to cluster my standard errors, right? In fact, here, let's say I did, yeah, so that's why I went back up here. Let's do, I'm going to get rid of my two-way fixed effects just to kind of give you an example of it. So let's say I just included my fixed effects for the state county. I would kind of come up with this. Let's say I wanted to adjust for it. And this is where, let's see if I can remember. I think it's FE and then VCE. See if I can remember the syntax off the top of my head. I might have these flip-flopped. Oh, I capitalized things correctly. So you can kind of see without clustering, I get a coefficient of negative 0.24, standard error 0.003. Same coefficient if I cluster, my standard errors are a little bit higher. Now, in this case, it doesn't matter because my p-value is 0 in both cases. But why do I actually know I was less likely to reject the null here after clustering my standard errors? So my test statistics negative 30. What was it before? Negative 74. So even these both look like 0. Which p-value is actually smaller? This one, all right? Because I have a slightly larger, more than twice as large test statistic. Okay. But there's no reason to just automatically cluster your standard errors unless you have that test and you fail to reject that there's autocorrelation, right? Unless you can't reject that it's different than negative 0.5. In this case, we didn't, so there's really no reason we need to be clustering our standard errors. It would be accepted by like other economists, et cetera, data researchers. You don't need to cluster your standard errors if you run this test and you can't say that the autocorrelation in your error terms is anything, or the correlation in your error terms is anything different than negative 0.5. All right. So instead of working through an additional example, I might hold off on this till next week, just kind of save it so we can run through another one. One thing I didn't show you today, so we have these LDOT commands. There's actually some easier ways we can do this, which is this DDOT command. So it does a very similar thing. But I also think it's worth mentioning, since we did talk about this. I don't know what other classes you guys have taken. So have you guys taken like who's taken like some upper level macro courses? Yeah, so you might not just care about the previous time period. What might be another really good indicator? Not what just happened last year, but what happened 5 years ago, right? There's some things that we know the effects take a long time to play out. So we might not just want to use, so you don't have to only use this lag system in order to do fixed effects. Maybe this is something like, I'm trying to predict the unemployment rate, and I think that the income levels from last year matter. But I also think, well, let's do this. Let's say that I don't think, I could even do this. Let's say I just wanted to say, the thing that I think is currently impacting unemployment rate the most is what the income level was 2 years ago. That it takes income changes 2 years to actually play out, for us to actually see it in the unemployment data. I can run these regressions where I use this twice lag. So this will go back 2 time periods. And now I can pick up what's the relationship between unemployment rates and what average incomes were in that state county 2 years prior, right? So I can start to include these additional controls as well. So I can go back and say, why do we want to use, what else is in this data set? Well, I guess I dropped a bunch of it just to make it smaller. If I had other variables, I could do like L5. What was the, oh, what's a good one? Maybe I have like, and let's do L4 because this makes a little more sense. Was there a Republican or a Democrat in the political law and in the presidency 4 years prior? Because anything they did, it's still going to maybe play a role for you, right? So I can use all these different variables that I want to use typically as controls, even dummy variables, but I can lag them and go back as many years as I want to. Right? Now, we won't do a whole lot with that in this class, but if you're thinking about like, you know, financial markets and making predictions for stock prices, they start using all kinds of different levels of lags, right? So you'd be using this type of coding a lot because you're going back not only the previous time period, you know, I don't even know enough to know enough about what they're doing, right? Like they'll be using some random variable that's supposed to predict movement in this specific industry, but really it takes 30 years for it to, you know, bleed out into the actual industry, right? Whatever the political regulations are or something like that, right? So you can go back as many time periods as you want and include these as additional controls, right? It's just for what we're doing with fixed effects, all we really needed was the once lag, right? Is that making sense what I'm saying there? If you really wanted to do that. So got another example. We'll kind of revisit some of this autocorrelation stuff at the very beginning of class on Tuesday. We're then going to jump to, I don't think I put it up here yet, but instrumental variables. So it's the last topic that we'll cover. It's another way that we have of, if we don't have panel data, how can I eliminate omitted variable bias without obtaining data on the actual omitted variables, right? Here, we didn't need the omitted variables. We could just include fixed effects that accounted for time invariant things. Well, what if we have things that aren't time invariant that we still want to control for? We can't use fixed effects, but we can use instrumental variables. So we'll talk about those next week. Other than that, problem set and quiz due by the end of the day tomorrow. Any questions for me before I let you guys get out of here? All right, have a good Easter weekend. Be fun, have fun, be safe, and I will see you guys on Tuesday.